G'day nerds. In this video we are going to look at how to calculate the enthalpies using Hess's law. In it though, we're only going to look at the calculations only. There's no explanation of what Hess's law is, straight calculations using both cycles and the equations method, but no explanation of what Hess's law is. If you need an explanation of Hess's law, I've got a complete Hess law video. Just watch the first part of that. Actually, that's all of this. So watch that, then continue through the calculations on that one as well. If you're just looking at how to do the calculations, this is the video for you. So our goal in this one, again, is just to be able to do the calculations enough that we can find some online and go do some practices. If you're really trying to nail it and work out your best way of doing this, I would suggest every question you do one cycle, then the equations, then with the next question do equations, then the cycles, until you get the feel for what's your best way, which one you prefer. You need to be able to do both, but you need one which is just your go-to until you realize that you need the cycles or whatever. So this video, just the calculations. Let's jump into it. Alrighty, so here we have a question. These are all IB questions. So 2-methyl-propan-1-ol can also be converted to produce diesel and jet fuel. The first step of the process is the production of 2-methylpropylene, and here we go, propanol to 2-methylpropylene, propene. It gives us water over here. Using the data below, calculate the enthalpy change, and you'll see that they've given us a bunch of equations. Here we have 4 carbons plus 5 hydrogens plus half an oxygen goes to whatever that is, doesn't matter. What's that? 2-methylpropan-1-ol, because it's up here. And here we have our what it's used to make the 2-methyl propene, and here we have the steam. Now what you'll notice is that each one of these is the elements, and each one of these is the elements in their natural state. So here we're technically using the enthalpies of formation, which means we could find these in a table, but they've been nice and they've given us the equations to go. So this is our target equation. Okay, we're looking for X kilojoules per mole of that one. So we write out our equation as we're going. This is our target equation. So I know it's already up there, but we're going to write it out so we can structure it out in the way that works for us. Then we're going to write down all of our products down here. So all our elements. So we need, this is going to be in the equation, this is going to be in the equation, this is going to be in the equation. Gold. Nice, not a problem. This is actually a pretty straightforward one. There's no multiplying of coefficients and stuff to come. So as we get ready to do this cycle, let's have a look. We know that we're going enthalpies of formation. So let's actually, we'll label these. So we've got a little blue star, green star, and a red star, or pink star, I suppose. Our first one, we take it straight from it, minus 335 kilojoules per mole. See, all of the stuff in this equation is down here, and it goes up to that. When you're using enthalpies of formation, you actually don't need to balance it down here. You've just got to balance it up there. That's the important part. Our next one is minus 17 kilojoules per mole. Notice how it's changed direction though. Like this one's going up that way, and this one's going up that way. And the next one is going to be minus 242 kilojoules per mole. So, nice, fun. We've got our little cycle. And now here comes the hard part. Just jokes. It's pretty straightforward. What we do is this enthalpy is the same as all of these summed up. But look at the direction of that arrow. These two go in the direction of that arrow. Gold. This one goes against the direction of that arrow. So what we'll need to do is we're going to have to revert that, and we'll see that in a second. So due to Hess's law, X equals Y, or X equals the sum of Y's, because it's a stack in there. So it equals 335 plus minus 17 plus minus 242. But you notice again we flip the sign here, and that's because it's going against the flow of delta HY. And yeah, so we just add those together. Boom, done. that's it. 76 kilojoules per mole. That is the enthalpy of this reaction right here. Endothermic reaction, exothermic if it's negative, endothermic reaction, done. First cycle complete. Let's have a look at how we would do this as equations. Okay, so boom, target equation, gold. We're looking for delta H equals X kilojoules per mole. We want to rearrange these equations down the bottom here to match the target enthalpy up here. So I'll show you what that looks like. It's kind of fun. So we write down our target equation, done. I'm going to label all these A, B, C with a different color. Now have a look. So here we have our 2-methylpropane-1-ol, which is a reactant, but here it's a product. So if we're trying to get it to match this thing, you'll see what I mean in a minute, we need to change the sign of this. We need to flip it. And if we flip that, we have to flip this. That's important. That's a very easy place to get caught out. So we're now going to write A down here, right? See how we flipped it, which means we flipped that. Keep that straight. All right. Good. We've got that written down. Now go for B. Okay, that's this one here. Here we're going for the 2-methylpropene. It's on the right side, so we don't need to do anything to it. And we write that down there. Super duper good. Nice and straightforward. Then we've got our C right here. H2O steam. It's on the right side. Don't need to do anything. So we're just going to put that there. Minus 242 kilojoules per mole. So now comes an important step. It's not important for the calculations of it. It's important for checking that we're doing the right thing. We need to start cancelling out our steps, extra components, to make sure we've got just what we need. All right. This 4C over here cancels out that 4C. These hydrogens plus these hydrogens gives us 5. That cancels out that hydrogen. This half an oxygen cancels out that half an oxygen. So far, so good. And what we see that we have left is we have just the 2-methylpropane-1-ol, the 2-methylpropene, and the steam. Good. That's all we need. Okay, we've got everything we need. Bang, it all works out. Our working's going to be good. So, because delta HX equals the sum of ABCD, or ABC, right, all the way across, we just have to add them together. 335 plus minus 17 plus minus 242 gives us 76 kilojoules per mole. That's it. A nice and straightforward one. Let's see what we've got next. All right, so our next cycle. When in danger, bombardier beetles fire a hot toxic mixture of chemicals at their attacker. Kind of cool. Not kind of. That is cool. The mixture contains quinone, a really important thing for the British Empire and how they took over the world. A compound, C6H4O2. This is a compound that is formed by the reaction of hydroquinone and C6H4 hydroxides, 2 of them, with hydrogen peroxide. The equation for the overall reaction is C6H4OH2 plus hydrogen peroxide aqueous plus goes to quinone plus 2 waters as a liquid. Now, I've got a tricky step here, and this is our target equation, right? We're happy with that. And we're going to do this in the cycles. So, first off, you'll notice that we can get largely down, here we've got some of the elements involved. Here we have a different reaction involving these. Plus then we've got the steam here. So let's have a look at how we're going to set this up. We also need to watch out for this coefficient. Anywhere that we need to include water, so this is not something that gets cancelled out, right? Like, this is part of our deal. Anywhere that needs to include this water, well, it's water at this point, steam down here, has to be doubled. That's important, which means the numbers here are going to double as well. So, write down our target equation, all right? Then we're going to put down this equation. So here's all of our components that exist in all of these except for this one. This one's rude. And we'll sit there and draw how these work. First off, we need to also put our water as gas in the middle, right? So we can tell that we can go from this via that. We need to put that step in the middle. So you got to plan these out a bit. So we've labeled our blue, green, pink, and yellow. And that's just to show you where each line's going to go as we do this. All right, first off, blue. We come down here. This is plus 1774 as we write it down. Bang, going this way. Remember, this is pathway A, this is pathway B. All right, so we've got that. Goes down here to produce this plus hydrogen. Sweet. Then it goes up to there. So that's all still there, right? Like, that's showing you that this is up to there. It doesn't have any enthalpy change because it's staying exactly the same, but we've drawn it down the bottom there. Alrighty. Here we have hydrogen plus oxygen goes up to produce our hydrogen peroxide. Okay, nice and straightforward there. Then we have our hydrogen and oxygen going up to produce water, steam, which then goes up to produce water. Now, again, you notice there's a 2 here, and there's one there, and one there. So we have to double these values. So it becomes 2 to minus 241.8, and 2 times minus 43.8. All right, off we go. Now, next step, bang. We're going over this way, down this way. We're summing these up to give us the same as that. Okay, so let's just put them straight in. Plus 174. This is going the wrong way against our cycle because it's on the left-hand side. So it's going against our cycle, so we have to flip the sign up here. And then we are multiplying this by 2, adding that. Multiplying this by 2, adding it there. Popping them all together, we get minus 202.6 kilojoules per mole. That was a slightly more complex one, right? Still same process. We had to add an extra step here, and we had to add some multipliers. Same process though. But that's how it's done. So it's starting to get it. And you see they start to build up in complexity as you go along. Let's have a look at this one using just the equations. We won't do the cycles here. So, when in danger, the bombardier beetle can fire a hot toxic mixture of chemicals at their attacker. Excellent. Seems familiar. The mixture contains quinone, C6H4O2, compound formed by the reaction of hydroquinone, C6H4 2 hydroxides, with hydrogen peroxide. Nice. The overall equation is this. So we've got the hydroquinone plus hydrogen peroxide gives us quinone plus water liquid. Alrighty. Now, this is our target equation. Okay. We need to watch out for the coefficients. There's a double there. So anywhere where we have this 2, or this H2, and this H2O, so anytime we have these components, we have to double it, because that's what that means. So these values are going to double as we go. Alright, we write down our target equation. Smashing it. Then we're going to write down our other equations and make sure they're all facing the right direction. Okay, so this is facing the right direction. That's on the right side. We'll label them A, B, C, D. So equation A, perfect. We write down the plus 177.4 kilojoules per mole. No dramas there. We have a slight problem. Our peroxide is on the wrong side. It should be a reactant. So we're going to have to flip that. Okay, see, we've got the flip, the little signs there. So it becomes hydrogen peroxide goes to H2 plus O2, which gives us plus 191.2. So we've flipped the sign here as well. Then we have reaction C. We have water gas. Now it's not gas there, but it's on the right direction at least. So we don't have to flip this. But we do need to multiply it by 2 to get from our water gas. It's not the same. What do we do about that? So 2 H2s plus O2 gives us 2 H2 steams. We write that down. But that's not where we need to end up. So there's actually another step we need to put in there to go from steam to a liquid. Sweet, easy peasy. Remember, we've got to double it. It's in the right direction because we're going from steam to liquid. Write it down. Put it in there. Now all we have to do is sum up all these values, because delta Hx equals the sum of all of the other delta H's, and we put them in together. 177.4 plus 191.2 plus 2 times minus 241.8 plus 2 times minus 43. That's a minus. The maths still works out, I promise. Gives you minus 202.6 kilojoules per mole. Make sure when you write this out, you put a little minus there, because that comes from there too. It's fallen off. Yeah, so that's how we do it. Same process, a little bit more complex because we had to do some doubling there. We had to do some flipping and some doubling. And let's have a look at one more example. All right. What makes this one trickier is that it doesn't give us all of the equations. Okay, so we have to write some of those down. Let's look into it. Let's see how we go. First off, silane, a silicon hydride, is formed in the reaction of silicon plus hydrogen. Makes sense. Si solid plus 2 hydrogen gases gives us silane as a gas. Fun reaction, because you've got a solid turning into a gas when we add another gas to it. That's pretty cool. It's also not a reaction you can do in a school lab. So the enthalpy change for this reaction is called the enthalpy of formation of silane. So you can see that, right? Like silicon in its natural state at room temperature, etc., is a solid, a hydrogen gas. Boom, off we go. We're ready to roll. That's formation. That's using just the elements. However, it's a slightly rarer equation, rarer reaction. So we can't just look up the value for this. So we've got to do some other stuff. So the combustion of silane gives silicon dioxide and water. So here we have silane plus oxygen gives us silicon dioxide plus water. These are two we can work with. And they give us an equation for that. So the enthalpy of combustion of silicon is minus 911 kilojoules per mole, but you don't see an equation there, do you? But you probably know what the products of that reaction is going to be, right? The combustion of silicon is going to give you silicon dioxide. So use this information and the enthalpy of combustion for hydrogen in the data booklet to calculate the enthalpy of formation of silane. Here's where the water molecule is, so you can see where the combustion of hydrogen is going to come in, because hydrogen plus oxygen gives you water. And I've just pulled this out of the IB data booklet. The enthalpy of combustion for hydrogen, H2 as a gas, is minus 286 kilojoules per mole. So, a lot of question there. A lot of different things. We have to write some equations down. We have to come up with them ourselves. So, here's our target equation. The first thing we need to do, enthalpy of combustion of silicon is that, minus 911. There's the equation. All right, that's the direction it needs to be. Well, we'll see if that's the right direction in a minute. The enthalpy of combustion of hydrogen, this is the equation right here. And we'll note there's a 2 there, so we're going to have to double it. See, so we double that because it was half, so that goes up to just regular oxygen, 2 hydrogens, 2 waters, and we start to see that matches up. And if you'll notice, that is starting to match up with the 2 hydrogens up there. So that's fun. And the value there is 2 times minus 286. It's fun. It's fun. It's really fun. Okay. So let's put this all together. We're doing the equations method here, remember. So, target equation written down. This is the direction and the side that we need things to be on. Okay, silicon's going to be on this side, silane's going to be on this side. So, our first one, which is this one, it has to be flipped because see, our silane is on the left-hand side, the reactant side, and we need that on the product side. So, we write the equation like this. Boom! And we write plus 1,517. We had to flip the sign there. Important. Nailing it. All right. equation B, that's this blue one. Silicon dioxide. So, silicon dioxide, silicon plus oxygen gives us silicon dioxide. Now, this here seems to be tricky because the silicon dioxide is on the left-hand side, and we know that's right. But the silicon is on the reactant side of our target reaction. So this is the way it goes. So what that means is this step is actually an intermediate phase in the overall reaction if we were doing the cycles method. So we keep that at minus 911. Then we need to bring our water in, okay? So our water needs to be on the needs to be doubled because of this to get us to there, because again that's a middle step, so we want to get to there in the middle, which will then use that to get to there, and so on and so on. So we're at 2 times minus 286 kilojoules per mole, and then we're just going to add them together. That's all it is. So the sum, so enthalpy of X equals the enthalpy of these guys summed all up. We just put them in our equation. Simple arithmetic. 1,517 plus minus 911 plus 2 times minus 286 gives us 34 kilojoules per mole. And we're done. That's it. That's the whole box and dice. I hope that made a lot of sense. If you have any questions, any feedback, whatever, put them in the comments below and we'll get back to you as soon as we can. Thank you for watching. Hope to see you next time. Bye now.